Hello and welcome to part 3 in a series of videos I'm making in response to an open letter to deGrasse Tyson regarding the flat earth by dmurphy25. In this video I'm going to look at questions 2 and 3 because they're pretty much the same question. It's the same old thing that comes up like time and time again about curvature on water and why don't we see it and blah blah blah. Anyway, let's see what he says.
Question 2. Am I able to see the curvature or not? According to you, you cannot see the curvature even from a plane because the Earth is so big.
The Earth looks flat because 1, you're not far enough away at your size. 2, your size isn't large enough relative to Earth to notice any curvature at all. It's a fundamental fact of calculus and non-Euclidean geometry. Small sections of large curved surfaces will always look flat to little creatures that crawl upon it.
But apparently you can see ships disappear over the horizon. Now, the official explanation is that you cannot see the curvature across your vision. Apparently we see a horizon about 5 miles away. So in 5 miles there's enough curvature to see a ship disappear. Yet I cannot detect that curve over 10 miles because I can see 5 miles to my left and 5 miles to my right, so I've got an uninterrupted 10-mile span in which I should see enough curve to hide 2 ships, but I don't. So if I see enough curve over 5 miles, why don't I see it over 10 miles? Following on for that,
Right, this is just ignorance about geometry, that's all it is. And again, dishonest misrepresentations. First of all, this diagram here, why are you seeing 5 miles to either side? If your eyes were about 17 feet above sea level, the horizon would be about 5 miles away. If you were seeing 5 miles to either side, you would be looking at it with an angle of a viewing angle from side to side of 109 degrees. That's a massive angle of view. Now as well, you don't see a ship hidden at 5 miles away if your eyes are 17 feet above sea level. It starts to disappear 5 miles away. Exactly where it disappears depends on how big the ship is. So nobody's suggesting that you're going to hide 2 ships in 10 miles. That's just absolute nonsense. But anyway, what I'm going to do is we'll go with this 10 miles thing. So you're saying from 10 miles across, you're thinking you should see curvature. Actually, I want to say at this point as well, this is what flat earthers do not get. There's a difference between seeing the effects of curvature and seeing curvature. They're not the same thing. Seeing curvature is where you actually see something looking like it's curved. Seeing the effects of it is seeing something disappearing behind the horizon. It's not the same thing. You see the effects of curvature, you don't see the curvature. And I'm going to demonstrate how that works. Right. Now, a sphere has a cross section which is a circle. If you draw a line over the surface of a sphere joining 2 points and the line is the least distance between those 2 points, then that line will be an arc of a circle. So let's suppose we've got an arc over the surface of a sphere with a radius of 3,960 miles. An arc length of 10 miles. So say this is 10 miles. Now, let's make it clear as well. This diagram is visually not representative of the situation. It can't be because the curvature is too small to show on here. This is just to demonstrate what the numbers mean that I'm going to show you. But it's not what it looks like. Okay? So get that clear. This is not what it looks like. It's just to demonstrate. So an arc of 10 miles, that's 52,800 feet. So from here to here, that's 52,800 feet. Now this arc will curve very, very slightly away from a straight line going straight through the middle, straight through the circle. Okay? And we'll call it height, for want of a better word, is the amount that the arc deviates from this line here, which is what we call a chord. A chord is a straight line that joins one part of the circle to the other. The arc is the curved part of the circle. And it's very easy to work out what that should be. It's basically about 17 feet. Now you're beginning to get a sense of the numbers here. This is 52,800 feet. This is 17 feet. Now to get this in some kind of perspective, let's imagine that this is a meter long. One meter, which equals 1,000 millimeters. Okay, so that, say that's a meter long or 1,000 millimeters. This will then be about a 3,000th of that, 0.3 millimeters. All right, so to get a sense of how much a line on the face of the Earth 10 miles long would be curving, imagine a line a meter long, curving very so slightly, so that the middle of it is 0.3 of a millimeter deviating from the straight line. It wouldn't even be visible. That's how much curvature there is. Now let's go back to this. So this is 10 miles long, and this is 17 feet. So this means if you're standing here and your eyes are 17 feet above sea level, now remember this is practically straight, all right, so it doesn't look anything like this. So we'll just take it as being that you'd be standing straight up here, all right, although on this scale you'd actually be bending a little bit to that side. But so your eyes are about 17 feet above sea level. So you see to about here. Anything past here is going to be obscured by the curvature of the Earth. Now that means that something 10 miles away, the bottom 17 feet of it are going to be obscured from your vision. Not 2 ships worth. No one's suggesting that. Right? So if you look at this line 10 miles long side on, it wouldn't look like this. It would look like a straight line. If you're at one end of it looking along it and your eyes are almost right next to it, there's just enough curvature so that the second half of it is obscured by the curvature. So you see the effects of curvature, but you don't see the curvature. Can you understand that? Do you understand the geometry of it? It's practically flat. There is a very, very slight curvature. Just enough so that if your eyes are just a few feet above the surface of the sphere, okay, now remember, 16 feet above a sphere with a radius of 3,960 miles is not very much. Your eyes are right on the surface of the sphere. You're just starting to see things disappear about 5 miles away. But everything will look flat to you because of the scale of it. Right, let's have a look at what he says next.
But I don't. So if I see enough curve over 5 miles, why don't I see it over 10 miles? Following on for that, question 3, why haven't we ever seen curved water?
It's basically the same question, but let's go on.
If the Earth bends the water into a sphere around it, then if it was to freeze suddenly, we should detect a hump in the water, shouldn't we? So why is it that when Lake Baikal in Siberia freezes over, it is one of the flattest places on Earth, despite being 395 miles long and 49 miles wide? There should be a hump in the middle of it, nearly 20 miles high. So why haven't we ever seen curved water?
Right. Oh, there's so many misrepresentations. First of all, it's wrong to talk about it as being a hump. I've looked down here. If the situation looked something like this, where the vertical went straight up like that, then it'd be meaningful to talk about this being a hump. But that's not what the situation is. The situation is like this, where the vertical is pointing away from the centre of the Earth. So what direction is vertical depends on where you are. So if you're at point B, vertical is straight up, and the Earth is curving away down from you towards C. If you're at point C, we put C at the top now, then vertical is straight up, and the Earth is curving away down towards B. Therefore, it's a bit of a misrepresentation to call this a hump. Let's look at the figures that he talks about. So he talks about this stretch of water, which is described as being very flat. Now, I'll just touch on this point as well. When people talk about part of the Earth being very flat, they don't mean that it doesn't have curvature. They mean that its elevation profile is flat. All right? So that would mean that, let me bring this up, that all of this would be considered flat because it's all got the same distance from the centre of the Earth. And wherever you are, the vertical is relative to that position. And because what you only see a tiny amount of the Earth at any location, what you see is locally flat. So that's why we talk about it being flat. It doesn't mean that there's no curvature. But let's go back to this and talk about the figures that he uses. So it's 395 miles. And the hump, or the height, whatever you want to call it, is 5 miles. You got that right. He initially said it was 20, and then he corrects himself. So his numbers are correct. So once again, let's compare this to a meter, 1,000 millimeters. Well, this means that the height here would be 1.2 centimeters. 1.3 centimeters. A curvature that would be noticeable if you saw it, but still very, very slight. So imagine a line a meter long that then bends very, very slightly. So the middle of it is bending 1.3 centimeters away from the straight line. That's how much of a hump we're talking about over 395 miles. Absolutely tiny, a tiny little bit of curvature. And like I said, any one part of it, you're only seeing a tiny amount. Now, the smaller an arc length you take over the surface of the Earth, the less curvature you're going to see. Okay? The smaller an arc length you take of a circle, the closer that arc length approximates to a straight line. That's what we call locally straight. Now, this would also apply to the surface of a sphere. If you cut out a circle from a surface of a sphere, the circle will be slightly curved. Now, the amount of curvature it's got depends on how big a circle you cut out. If you cut out a very, very small circle, it's approximately a flat circle. That's what we mean by locally flat. The smaller a part of it you take, the closer it approximates to being perfectly flat. Just like this arc length here. If you take a very small arc length, then it's almost exactly a straight line. You take a bigger one and you get more curvature. So like over 395 miles, it's kind of like a meter stick bent by 1.3 centimeters in the middle. If you take it over 10 miles, it's like a meter stick bent by 0.3 of a millimeter in the middle. It's much less curvature. So this is why wherever you are, it looks flat, because you don't see very much of it. And like I said, this isn't really a hump, it's just the curvature, and it's very, very slight. It doesn't look like this. It would look like a tiny amount of curvature. Okay? So that's dealt with questions 3 and 4, which are questions 2 and 3, which are both basically asking pretty much the same thing anyway.